Hi there, Dr. Scott Stevens here, and today we're going to be talking about discrete probability distributions, in particular how to work with the cumulative distribution. This video, although short, is actually a pretty big deal because it turns out we'll be using cumulative distributions for the rest of the course. So understanding how they work, and in particular how they work with discrete distributions, is going to be pretty important. I can tell you right now that messing up with discrete distribution, cumulative distributions, is one of the most common mistakes that you'll see in the upcoming tests. So it's worth paying attention. So let's get started. What do we mean by a discrete probability distribution? Well, it's not very much of a new idea for you. You'll remember that back in chapter 2, we talked about how to build a frequency distribution by counting how many times each possible outcome came up, and a relative frequency distribution by dividing each of those numbers by the total number of trials. So in my data here, I've got data from rolling a six-sided die 80 times, and as you can see, it ended up coming up with a 1, 12 times, which was pretty uncommon, but it came up with a 2, 18 times, which is fairly common. To figure out the relative frequencies, I take these numbers and I divide them by the total number of observations, which is 80, to get the relative frequencies. So this was the result of my 80 rolls. Of course, in a fair die, you'd expect that in the long run, those numbers would all be the same. And indeed, with a fair die in the long run, they would be. But randomness means that for only 80 rolls, we don't expect them to balance out perfectly. A probability distribution tells us how likely it is in the long run that each of these things comes up. Sometimes we've got nothing better than a relative frequency distribution to work with, but sometimes we can do better and actually have a table which tells us the exact value, in this case the classical probability, of each one of the outcomes. So basically, you won't go very far wrong if you interpret a probability distribution the same way you interpret a discrete distribution. Notice that what I've got here is a list of all the possible different values that can appear and the chance that each one does. I can do this because I can actually possibly list every possible value. For a discrete variable, you can in theory do that. For a continuous variable, you can't. For example, with all the numbers between 1 and 2, how would I possibly write them? They're an infinite number. That's something different that we'll do with continuous distributions, but that's going to be in chapter 6. Right now, we're talking about chapter 5. Okay, I want to remind you not just about the idea of a relative frequency distribution, but also of a cumulative relative frequency distribution, which meant simply keep a running total of how much you've got so far. Here, how often do I roll the number 1 or less? Well, it's impossible to roll 1 less than 1, so the chance of getting a 1 is the same as the chance of getting 1 or less. How likely is it that I roll a 2 or less? Well, 1/3 of the time I'll roll a 2 or less. 1/2 the time I'll roll a 3 or less on a die with 6 sides. But this column's really easy to generate from any probability distribution simply by keeping a running total. This number plus this number is this number, the sum of these 3 is this number, the sum of these 4 is this number, of these 5 is this number, and the sum of all 6 is, of course, 1. When you're dealing with cumulative probability, that last entry is always going to be equal to 1, because there's a 100% chance that on a die, for example, I'll get a roll of 6 or less. Okay. Notice, by the way, that if you do have the probability column, as we just said, it's easy to get the cumulative by just keeping a running total, but something which might not be as obvious. If you start out with the cumulative column, then you can recover the probability column just as easily. Let's see how. We've already said that the chance of rolling a 1 or less is the same as chance of rolling a 1, so that those two are exactly the same. On the other hand, if I know the chance of rolling 2 or less, and I subtract off the chance of getting 1 or less, well, that gives me the chance of getting exactly 2. 33% of the time I get 2 or less, but 16% of that is getting a 1, which means that the other 16 or so is made from getting a 2. And I can keep on playing that game. How likely is it that I get a 3? Start with the probability of 3 or less. Then subtract off the probability of 2 or less. Everything from 3 on down, take away everything from 2 on down, it just leaves you the number 3. And of course you can play this game with the rest of the table as well. The difference between two successive cumulatives tells you the probability of exactly that many successes. Okay, fine. So sometimes we'll look at the probability column, and sometimes it's the cumulative probability. Depending on what kind of question you're being asked, one of those two will be easier to use than the other. Let's see what's going on with this with a different example. I'm going to talk about the game of Keno, particularly the way that it's played in the West Virginia lottery. Keno works like this. There are 80 different numbers that you could possibly pick. And if you want to play Keno, you pay your $1 ticket, and then you pick some numbers. You can pick anywhere between 1 and 10 numbers. To make things simple, I'm going to assume that you pick 10. So the 10 red numbers that you see here are the 10 numbers that this person picked. After you pick your numbers, West Virginia is going to go ahead and pick 20 numbers out of those 80. All the check marks that you see in this chart are the 20 numbers that they picked. You get credit every time that your number matches one of the ones that was picked. So here, this person picked a 6, which was one of the 20 numbers picked, so that's a match. Here's a second one, here's a third one, here's a fourth one. Out of the 10 numbers they picked, they had 4 matches. So what's that do for them? Well, sorry, it turns out that if you look at the payoff schedule, it takes 5 matches to win, not 4. So this person would end up having a losing ticket and would have spent it all around nothing. But let's take a look at this from the perspective of probability. It turns out that I can figure out all of these outcomes of how many matches by using classical probability. The calculations are a little bit complicated, and feel free to call me or talk to me if you're interested in knowing how, but it can be done, and here's how it came out. Let's make sure you understand what you're seeing here. A couple of questions. What's the most common number of matches? Hopefully you said 2, because 29% is the biggest one. Almost 30% of the time you'll get 2 matches. How often do you get 2 or 3? Well, hopefully that's a pretty easy question for you too. Just at under 30% of the time you get 2, and just over 25% of the time you get 3. So if you add those two together, you get about 55%. So a little over half of the time you'll have 2 or 3 matches. We had 4 in our particular example, and as we can see, that happens about 14.7% of the time. But I could ask more complicated questions. For example, in this game, it turns out you don't get paid if you get a 1, 2, 3, or 4. How often would that happen? What calculation would you do? I'm betting you got it right. You'd take that number, plus that number, plus that number, plus that number. If you want to be formal about it, it's because these are 4 disjoint outcomes. You can't get a 1 and get a 2 at the same time. They're disjoint, so their probabilities add. And that's true with all 4 of these. So I could add those 4 numbers to figure out the chance of not winning any money. But I don't feel like adding those numbers. Adding 4 numbers is never fun, and these ones are really long. But I can do better if I've got the cumulative distribution. Let's take a look. Here's the cumulative column. I want to know what's the probability of getting a 1, 2, 3, or 4. Well, I'm going to look right in this row right here, and in particular, I'm going to look at this number right there. That's almost what I want. That number tells me that the chance of getting 4 or less matches is 93.5%. But that's not quite what I want. I want 1, 2, 3, or 4, not 0, 1, 2, 3, or 4, which is what that number means. So I have to subtract off some. How much do I have to subtract off? I'm hoping you said it's right there. That's the chance of getting 0 matches or less. So if I take 4 or less and subtract off 0 or less, then I get exactly 1, 2, 3, or 4. And that comes out to be about 89%, which is pretty heavy duty. It says that 89% of the time, or 8 times out of 9, you actually end up losing and not making any money at all at this game. That's how the state makes money from it. Okay. This in a more general context. Suppose I wanted to know the chance of having somewhere between 5, 6, or 7 wins. That's something in this part of the table. Well, I could start out by saying how likely is it that I get 7 wins or less? And as you can see, it's really quite likely, about 99.98%. But I don't want everything from 7 on down. I only want the things that are 7 and 6 and 5. That is, I don't want to include the numbers 4 or 3 or 2 or 1 or 0 in this total. This is 7 or less. I'm going to subtract off 4 or less. That means take everything from here on down, which is fantastic, and then subtract off or get rid of everything from here on down. And when I do, the 3 things I'm left with are these ones right here. I want you to notice what we did though. We took the biggest number that we wanted to keep, 7 successes, and we subtracted off not the smallest number we wanted to keep, but instead the biggest number that we wanted to get rid of. Biggest thing I wanted to keep, 7. Biggest thing I wanted to get rid of, I wanted to keep 5, but I didn't want to keep 4 successes, and so that's what I subtracted. This is absolutely huge, and this is the mistake that almost every student makes when you test them on this stuff. So keep it in mind. This rule is a big and important one. Okay? There are some cases where you don't have to do the subtraction. If I wanted everything from 4 on down, for example, there's no need to do a subtraction. That number is the probability of 4 successes on down. So if I want 4 or less, that's my answer right there. What I'm subtracting off is the biggest thing I want to get rid of, and there isn't anything, so I don't subtract anything. The other case can happen, though, when you want all the numbers that are bigger than or equal to a cutoff, like 4 or more. Here, the biggest thing I want to keep is 10, and the cumulative for that is 100%. The cumulative for the biggest possible value will always be 100%, because you always end up with a value that's that big or smaller. That means in this formula down here, the biggest thing that I want to keep is going to be 100% probability, okay? Like this. The biggest thing I want to get rid of? Well, if I want everything from 4 on up, the biggest thing I want to get rid of is the value of 3. So I'd say 1 minus cum of 3 would tell me the probability of 4 or more matches. Okay? All I'm going to say in this video, but I've gone back to the previous slide because it's absolutely essential that you understand what this rule is and how it works. So just in case you didn't, you might want to watch this again. It's really, really important. Thanks.